Sound, or sound waves. To review once again, waves are vibrations that transmit energy without transmitting a physical material. Sound waves are mechanical waves. They require a medium. The medium can be solids, liquids, or gases. The most common medium we think of for sound is air. Sound travels nicely through air, but it can travel through liquids like water and solids like steel. We'll talk about that a little bit more in a minute. But sound is probably our best example of a longitudinal wave, a wave in which the particles of the medium vibrate parallel to the way that the wave is transmitting. Now I have a couple diagrams down here. I'll start on the right-hand side. The right-hand diagram here, it's a little bit dark, is supposed to be a tuning fork. The white dots are supposed to be air particles. And you can see sort of a pattern there, and I'll kind of highlight it with red. These circular regions here are what we call compressions. The air has been compressed by the vibrating tuning fork. They would be analogous to crests for a transverse wave. As you can see here on the left, I'll kind of match those up. We have compression, compression matching up with crests of the longitudinal wave, or the transverse wave here at the bottom, the sound waves at the top. On this left-hand diagram I just highlighted, with the speaker on the left and the ear on the right, the black dots are the air particles, and the air gets compressed. Now one thing about sound is it travels out essentially in all directions. When I'm talking, or the speaker here, or the tuning fork on the right, these are two-dimensional diagrams, but in real life sound travels spherically outward from the source. So even when I'm facing forward, the sound waves travel up to my left, to my right, and behind me in like spherical shells around my head or my mouth. The diagram on the left maybe is a little bit misleading because it just shows the sound waves going in one direction straight from the speaker to the ear, but it's cutting out all the three-dimensional aspect of the waves surrounding the entire speaker. Now once again, you can kind of focus sound in one direction, so the speaker might be strongest or the loudest as it faces to the right towards that ear, but the sound waves would travel out in spherical shells around that speaker. Anyway, so the air particles get compressed, so we call those compressions. So sometimes sound waves are called compression waves. And between the compressions, where we have tightly packed air molecules that I've marked in these two diagrams, you have what are called rarefactions, where the air has spread out and it's lower pressure than standard atmospheric pressure. If you average this all out, you took away the compressions and rarefactions, you would get standard atmospheric pressure. Anyway, sound travels at 344 meters per second in the standard normal room temperature. Let's take 70 degrees. That's about 769 miles per hour. I'm not going to make you memorize that. I will give that to you on a test. But it does travel faster in water. It travels about 5 times faster, well, 4 and some fraction times faster in water, about 3,300 miles per hour. It travels even faster in steel, about 13,000 miles per hour, or 5,800 meters per second. Part of the reason, or the main reason why it travels faster in water and steel is because the particles that have to bump into one another are already closer together as they are in the structure of a solid or a liquid. In air, the particles are already far apart, and it takes a little bit longer for them to bump from one to another, because remember, in all cases, once again, it's only the energy that's transmitting because the air particles or the medium particles, the steel or the water, have to bump into one another to transmit the sound. You're not actually transferring particles from point A to point B. Once again, sound waves are a very good example of longitudinal waves. All these air particles are vibrating forward and backwards in the same direction that the wave is propagating. But when you study these mathematically or with all the terms and vocabulary, it's the same thing as studying transverse waves. Going back to this diagram on the left here, at the bottom we have a transverse wave, crest and trough, crest and trough, crest and trough. Well, the crests match up with compressions of the sound waves, and the troughs of the, I'm using these black lines to represent the matching of the rarefactions of the sound waves with the troughs of the transverse wave. And you would measure the wavelength the same as you would with transverse waves. You could measure from compression to compression, like if I use this here at the top. That would be the wavelength, lambda. Literally, I can measure that if I could see air particles. But in this diagram, I can see the depiction of the air particles. That would be the wavelength in meters from crest to crest, or from compression to compression. But you could also measure wavelength from trough to trough, as long as you're measuring from the same corresponding trough or rarefaction of one wave to the next. That would be the wavelength. Pitch is a reference to the frequency of sound waves. The average human can hear from about 20 hertz to about 20,000 hertz, at least when you're young. When you're older, you start to lose some of the ability to hear the higher frequencies, or if you've had some ear damage from loud sounds and so forth. Sounds below 20 hertz are called infrasonic. They're below our human hearing range. And if they're above 20,000 hertz, they're generally called ultrasonic, above what we can hear. Now, there are some animals like dogs that can hear sounds above 20,000 hertz. The loudness of a sound is measured in decibels. Now, the decibel scale is logarithmic, and it's kind of like exponential. It increases faster than you think. For example, a 70 decibel sound is 10 times louder than a 60 decibel sound, 10 times more intense, so to speak. An 80 decibel sound is 100 times more intense or louder than a 60 decibel. 90 decibels is 1,000 times, and you'll start to see a pattern here. 90 decibels is 1,000 times louder than 60 decibels. In other words, from 60 to 90 is 30 decibels. The key there is the 3. It means 3 zeros, so 10 to the third is 1,000. Same example, or to extend the pattern, 100 decibels is 40 decibels bigger than 60 decibels, but the 4 is the key. There's 4 zeros. In other words, 1, 2, 3, 4. It's 10,000 times louder or more intense than 60 decibels. So here's an example. If you have 80 decibels, it's 1,000,000 times louder than what other sound intensity or sound loudness? Well, that's 6 zeros, 10 to the 6, or to work backwards here, that would be 60. 80 minus 60 is 20. So 80 decibels is 1,000,000 times louder or more intense than 20 decibels. On the right here, I have a table of some common sound levels with a threshold of audibility at 0 decibels, a very quiet rustling of leaves, 10 decibels. An average whisper at 4 feet is 20 decibels. Keep in mind, all of these numbers also depend on how far away you are. So if you're farther than 4 feet from a person who's whispering, the sound will not be 20 decibels, it'll be less than 20 decibels. And if you're real close to the person, they're whispering right in your ear, it might be higher. Well, it would be higher than 20 decibels. They depend on how far away you are. And they're somewhat subjective. You know, on a busy street, 60 decibels, well, it depends on the street or how far you are from the street. If you're right on a sidewalk next to the street, okay, average street, 60 decibels. Obviously, also, the loudness of a sound can cause damage to your ears. Now, it's painful, according to this table. Threshold of pain is around 130 decibels. I've seen in other tables like 120 decibels. It's painful. And this can cause damage to your ears in very short order. Those loud sounds, irreversible damage possibly. But even softer sounds like 100 decibels, which is still pretty loud. If you're in a factory, working in a factory that's 100 decibels, and you're in there all day long, 8 hours, 10 hours a day, you need earplugs to protect your ears, because over the long term, that level of sound can damage your ears. You've probably heard of Doppler Radar, and we use Doppler Radar to predict weather. It's based on the Doppler Effect. The Doppler Effect is an apparent change in the frequency of a wave due to the motion of the wave source or the wave receiver. Now, the Doppler Effect is most often applied to sound waves, but it applies to all waves. All waves experience the Doppler Effect. But let's use sound as our example. In these diagrams down here, here's on the left, the one with the car. Those circles around the car represent sound waves. Either the horn or the engine, car is giving off some sound waves, making some noise. If the car were not moving, all those sound waves would be concentric and evenly spaced all around the car. However, if the car is moving here to the right, which is indicated by this diagram, the sound waves, in that sense, bunch up in the front of the car. There's a higher frequency of sound waves in front of the car than there is behind the car. So there's a low frequency back here. I'll just say low F, low frequency back here. In other words, if you're a person standing by the side of the road, not in the middle of the road, if you're standing off the side of the road, you would hear a higher pitch noise from the car as you would over here. I like to use the race car example. If you ever watch professional racing when you have high-speed cars, NASCAR or the Indianapolis 500, and you're sitting in the stands or watching it on TV, you hear something like the following. There's like a high pitch as the car is coming towards the grandstand, and as the car passes you, it changes to a lower pitch. That's the Doppler effect. It's the change in the frequency. Now, the actual pitch of the sound has not changed, but the perceived pitch by the receiver has changed. Once again, the Doppler effect can apply to any waves, water waves, light waves, sound waves. On the right-hand diagram over here, I have, well, it's specifically referring to an airplane. And subsonic, over here, means below the speed of sound. Mach 1 means the speed of sound. The speed of sound is like 769 miles per hour, 343 meters per second at standard room temperature. What's happening here is this first diagram right here is a lot like the car on the left, and now we have an airplane, let's say, in the air. But it could apply to any wave source. But here, let's say it's giving off sound waves. A little arrow overhead view of an airplane in the air is traveling to the left. Once again, the sound waves given off by the airplane are bunching up in front of the airplane. So this left-hand diagram, when the airplane is subsonic, is a good example of Doppler effect. Once again, you have a high frequency of waves right here in the front, like it was with the car. High frequency of waves in the front due to the Doppler effect, the apparent shift in frequency of the actual sound waves given off by the airplane. And behind the airplane, there's a low frequency. Now, once the airplane, and airplanes can go very fast, they can actually, some, not all of them, but some, especially military aircraft, can get up to the actual speed of sound, Mach 1. So here's Mach 1, 769 miles per hour. All the waves now are bunched up right in front of the airplane's nose. So you have what is called a wave barrier, and you start creating what's called a shock wave because there's constructive interference. All those waves, those crests, those compressions for a sound wave are bunching up and creating a huge, huge wave. Well, once the airplane gets beyond that speed, now it's leaving all the sound waves behind. We have a supersonic situation over here on the right, and following the airplane is this V-shaped interference pattern. You can see it in the diagram. That's where there's constructive interference, where crest meets crest, or in other words, compression meets compression of the sound waves created by the airplane. For an airplane, that V-shape that I just drew is called the shock wave. It's three-dimensional. Once again, you have to imagine the three-dimensionality of this thing because an airplane is up in the air. It's like a cone following the airplane. You'll see this in the bottom diagram on the page. It's an interference pattern following behind the airplane, where the nose of the airplane is the tip of the cone. That cone that follows the airplane is really a sonic boom. It's a really high, intense, loud area following the airplane. Now, one of the misconceptions about sonic booms is that they only occur as the airplane breaks the sound barrier. Well, they're maintained as the airplane continues to go faster than the speed of sound. That sonic boom follows the airplane. I'll talk more about that in a second. It's not a one-time thing. It continually follows the airplane. But let me back up a little bit here once. The same thing happens with like boats in water. You have what's called a bow wave. It's just a two-dimensional version of the shock wave. You've all probably seen this with boats in water. You've ridden in boats in water. They have what's called a wake. It's a V-shape following the boat. Well, it's a basic area of constructive interference just like for the airplane, but it's a two-dimensional version. We don't call it a sonic boom, but it's a very large bump in the water, so to speak, a V shape. And it looks just like the diagram you see up above with the airplane. I'll highlight in blue again. This could have been a boat. And when you're water skiing, it's kind of fun to jump over that wake. You also have, when you're driving a boat, what are called no-wake zones, where you have to go slow and not create that V shape. And the only way you create that V shape is when the boat goes faster than the speed of the water waves it's creating. Because in either case, whether it's an airplane, it has to go faster than the speed of sound to create this shock wave, this boom, or for a water wave to be very loud or very tall, the boat has to go faster than the water waves, and it creates a very, very similar pattern to what you see in this diagram up here. For the boat, we call that the wake. It follows the boat at all times. It doesn't disappear. It follows the boat, just like the sonic boom follows the airplane. But you cannot see a sonic boom. You can hear it. These last two diagrams kind of expand upon the idea of the sonic boom following the airplane. Here we have, in this left-hand diagram, an airplane traveling this way at faster than 343 meters per second, which is the speed of sound in air, or 769 miles per hour. Faster than Mach 1. There's a cone. It's a hollow cone where the airplane is the tip of the cone, and that sonic boom follows the airplane. So, for example, they're showing trees down here, but I'll draw some people in here. If there's a person right here by this particular tree, they haven't heard the sonic boom yet on the ground. But if you're a person back here by this tree that's in the shaded region, that sonic boom has already passed that person. That person back over there has heard it already. Anybody right on this arc right here is hearing it right now. If there were people right there, they would be hearing that sonic boom as the airplane passed over you. And the loudness of that sonic boom depends on how high that airplane is. If the airplane's really, really, really high in the air, it's really not that loud of a boom. It's like a little more like a crack. But if the airplane's really low on the ground, that's a very loud sound, because the closer you are to a sound, the louder it's going to be. And it could even break windows at that level. Not always, but sometimes it does that. On the right-hand diagram here, we have a picture, and you can go to some of these websites I have listed at the bottom of the page to look at some more examples. But when an airplane breaks through the sound barrier, the air is so compressed, it usually creates these compression, these little clouds, these cone-shaped clouds, as the airplane goes beyond Mach 1. And it's kind of a cool phenomenon if you watch the videos at the bottom of the page. But once again, sonic booms follow an airplane. They're not a one-time thing. Just like wakes follow boats.